Thank you. Thanks for joining us today. So we have a 45-minute session. We're going to talk about resiliency. So let's get started. A brief overview of our agenda. So before we get started, let me give you an idea of how we are defining as our DR, right? Because DR has many definitions, right? Many people have different definitions of DR, most rightly so. As an example, a DR could be where you copied your data into a backup, and then you are able to restore your data in certain SLOs, and then you're able to continue your business, right? Mainly because of issues, failures that have happened, and things like that. And of course, on the funnier side, there are definitions like panic first, resolve later. This one I like, pray and hope your DR works, right? So our definition is basically have a business continuity. Effectively what it means is that you do not have, whenever there's a failure, your business continues to run with minimal to no disruption, right? With that as a definition, let's move on. So when we started off with our project on DR, our objectives were fewfold. Number one is to minimize overall downtime, whatever is caused by our DR. Like I mentioned, we want to have a business continuity. We want to make sure we support cloud, a third-party cloud, as well as data center environments. We do want to consider scale as a factor. We want to scale to thousands of tables, Iceberg tables, and data sets, right? So with that in mind, we have certain strategies that we built up, very in line with the community, and we're going to talk about it. I'll hand over to Lena to further give you more details on this. Right?
Okay. Yeah, thank you, Praveen. So first, we want to show what the challenge we are facing. We can see Iceberg table is very powerful. On the other hand, it's quite complicated. So the first challenge is how to make sure when we copy the data, we keep the data integrity. And also, the other challenge is in order for the business to continue, they don't operate on individual table. The table are dependent. Then how can we replicate the table in a way that's time consistent so the query can return the time consistent result? And performance is a big challenge. We spend most of our time on the performance. In order to reduce the downtime and also the data loss, we want to push the boundary to achieve near real-time replication. Therefore, the metrics of reduce the copy latency is our #1 metrics. Finally, is the cost. We don't want to break the bank in order to achieve all of these goals. Therefore, we have to address how to make sure it scale and still be able to achieve all of this. The next, we want to share what a strategy we have been taking, and hopefully that's helpful to you guys. First, it's like what object we want to copy. Database, that's for sure. And then the Iceberg table, that's the most complex part. Then the views we have to also replicate. The next one is performance optimization. It's an Iceberg table. However, we only replicate the schema. I will share more detail later on. So for the Iceberg table replication, there are multiple approaches. And then the approach we are taking is a commit-based approach. What I mean is, first, we detect the table has changed based on it's committed to the catalog service. Then we will start initiate the table copy. The table copy actually involves multiple steps because of Iceberg specifics. Once we finish copy, we want to verify the integrity of the data, then finally commit to the catalog service. have the Iceberg table, it's self-consistent. So the catalog service point to its metadata, and the metadata point to the data file, all of that in the same region. Then, once we replicate the table, we want to achieve the same structure, which means at the secondary region, the catalog service also point to the same region metadata, and then the metadata file point to the same region data files. In order to achieve this goal, we have 4 key steps. The first one is to identify the data. What's the file we need to replicate? Actually, when the table is first replicated, we don't need to do that because we copy the whole table. However, once the table is already replicated to that region, the second region, then we want to only copy the changes. That's where we have to detect, okay, what's the difference based on the versions at different regions, then compare the list of file in order. Actually, here there's an assumption. The assumption is once we copy, for example, the version 1 of that table in the second region, we don't need to worry about that. All of the version at version 1 and before, it's consistent, it has the data integrity. Then we only worry about new version we are going to copy. So this is very important. I will mention the access control to ensure this assumption is true. If this assumption is broken, then actually the table is broken. That's why it's very important to make sure data integrity is always maintained. Then the second one is the staging. Because Iceberg table it uses absolute file path. Therefore, when we copy the file blindly, actually the metadata file still point to the original region. Therefore, it doesn't work. And we use a staging step to rewrite the metadata file. That's what Ryan mentioned. That's one challenge for DR in the Iceberg. We have to rewrite so many files in order to make sure it's self-consistent still in the secondary region after copying. Then the next step is to transfer the files. Actually, we can transfer the list of the files in parallel to minimize the latency. The benefit is after we finish transfer, then we will verify those files. They are consistent with the original stage file. And therefore, after that, we will commit to the catalog service. That's the last step. Whatever we do before that, it's invisible to the reader. But with this atomic commit, then we can show, okay, this is the current new version. Now you can read it. With this step, we can make sure the data integrity, and also we are able to parallelize whenever that's possible. To summarize, this is how it looks like once we finish replicating the table. So in the, let's see here. So in the secondary region, we can see the replication. It always uses the region-based endpoint of the catalog service. This is our conscious decision. The reason is the replication is platform. We want to minimize dependency. Therefore, we want to specify for the replication job what's the source region, what's the destination region. It's very clear. Even for our naming convention, we make it very clear. So there are no mistaking. On the other hand, for the application, we actually use a global endpoint. The benefit for that is then application doesn't need to worry about what active region it's working with. Even before failover and after failover, the configuration for that application, they don't need to change. So that makes it much easier for the application. But as a platform, we want to make sure it's reliable. Then for the let's talk about the other replication object. So for the database, we need to make sure the database storage is also use a second region when we replicate the database. Um, Okay. So one thing that's very interesting is schema-only table. Iceberg has both the schema and the data. However, there are a lot of tables. They are for staging purpose only. There's no need to replicate data. When we make the changes to replicate only the current schema for those tables, we will achieve huge performance gain. First, replication latency is extremely small for those tables. Second, we avoid moving large number of data across the network. That avoids network congestion, free up the space for other application, and free up for other table replication. Okay. So here is how we orchestrate the failover and failback across different regions. There are two scenarios. The first one is planned failover. For that one, we know when the failover will happen. And to ensure we replicate all of the table first, we lock all the writes in the primary region. Then verify it's all replicated. Then we do the switch over. For the unplanned scenario, actually we don't know when that happens. In order to support this scenario, we actually to have the mapping between the application checkpoint and the Iceberg version. Then after the failover happens, we will say, okay, actually for this version, application only ran to this checkpoint. Then we have to rerun those that hasn't been copied to the second region in order to catch up. Then we can continue the processing. If you notice, if we are able to push the boundary, achieve the real-time replication, which means whenever the table change, we are able to replicate that, then the boundary between those two scenarios actually blurred. That's why it's so critical for us to minimize replication latency. That's how we can minimize the downtime and data loss to achieve our objective. So this is architecture for our replication system. The bottom line is a table level replication. Then the second one is cross-table. So that includes scheduling. How do we schedule the table to start replication? We will base on the resource available when the time the table has changed, and also how important to replicate this table to meet its specific SLO. Then the top one is the configuration. We will handle, like when the new table created, we will put into a group for replication. When the table got deleted, we will move it away. And also when there's dynamic traffic, for example, for some table, suddenly it has a large volume to how do we handle those? So this layer will handle all of these exceptions. In terms of the performance, there are several major factors we discover that affect our copy latency. The first one is the number of snapshots. When the table has many snapshots, the metadata file size is very big, and also it takes time to process those entries. Application team always want to keep large number of snapshots just in case. But for our purpose, we want to minimize the snapshots in order to lower the replication latency. Therefore, there's a give and take. And we want to see what's the best optimize the account. For example, we observe for some table that has frequent update, even reduce the snapshot number by 10%, we can achieve 40% reduction for the latency. So this is quite significant. Another one factor is overhead to start the job. There are so many tables are small, like 90% table, they can finish replication, incremental replication in 2 minutes. So if we just start a new job to replicate that table, that introduce actual several minutes, it's translate to 100% of the latency. Therefore, we have to be really careful how to minimize in every way we can to minimize replication overhead. We want to have a long-running job. Once it detects the table can be started, we are able to start right away without restarting any other resources or processing. Finally, this is typical. For S3, they have a rate limit on how many requests you can ask in parallel. So this is networking related issue, and we need to be careful about how to design the table to avoid this kind of bottleneck. Finally, it's a cost. We found majority of the cost for this replication is due to the egress traffic. The cloud provider, they charge a lot for this. I highly recommend to look at how to route use the private network to minimize this type of cost. Then for the compute, as I mentioned, we want to have a long-running job that continuously replicate multiple tables. In this way, we can minimize whatever overhead associated with replication. There's another big, it's the operational cost. We want to automate a lot of processing to handle those exceptional situations, especially when we know exactly what's going on. So self-healing is important. After I talk about what's our approach and recommendation, this is another alternative approach. That's a continuous replication. What I mean is, instead of has customize and rewrite all the metadata paths, this approach actually avoid it. It will have the catalog replication and also has the metadata and data file replication use a storage replication. Then, instead of use absolute file path, it use a multi-region access point. So the benefit is it works in AWS. You don't need to develop your custom solution. And also replication is low latency. However, the problem is there's no coordination. It's possible once the catalog already show in the second region, the version 2 is available, but corresponding data or metadata file, they are not fully covered. So actually the table in the corrupted state, but it's already visible to the reader. This is quite dangerous. That's why we decide not to take this. The beauty for our approach is, yeah, it's heavy lifting. But on the other hand, it doesn't leak the complexity to the reader. The reader is simple. So for the things to consider when you build your solution, first, we need to pay attention to the table divergence. What it happens when the destination table is out of sync with the source table. However, there's no clear path how to reconcile, how to bring the destination table to the source table. And the impact is there could be data loss or data corruption. So we need to detect the scenarios when those situations happen. The first one is there's no lineage. So the primary table doesn't keep long enough history about the metadata change. Therefore, the version of the destination version is not covered in that history. And therefore, there is no clear path how to reach from destination to the primary region's version. The second example is the metadata file is not consistent. So for example, in the source region and also destination region, they have the same version of the table. However, their UUID are different. So obvious something is not agreement. It's not consistent. We have to handle how to for that situation. The first approach, we want to prevent this from happening. And we want to replicate frequently. In this way, we can avoid the lineage issue. Another approach, we can increase the history we log in the primary region table. second region, it's okay to be read. However, only the replication job can copy the source table to destination. Nobody else can touch the destination table. So this is very important to avoid data corruption. Okay. So for observability, we have very extensive metrics to track what's happening on the copy pipeline level, on the database level, on the table level, and even for a table, we will show the important message to observe what's happening if that table has any issue. And then we will trigger alert if the problem happens. So finally, we want to talk about what's the next step for the DR solution. There are several important features we would like the open community to consider. The first one is support the relative path. Ryan also mentioned the V4, right? There are a lot of benefits to avoid the rewrite. But on the other hand, it's give and take. When we avoid one problem, usually there's another problem pop up. What I mean is, this introduces dependencies. So if you don't manage that correctly, if you don't have very precise coordination, you could accidentally delete the data. Or you can, for example, point to the wrong data. So manage reference, manage integrity become even more complex. The second one is timeline. Like we mentioned, the table are not exist by itself. For application, usually deal with multiple table at once. Then how can we make sure in the second region, they still show the consistent result? For us, we can use scheduling to pace how we replicate the table to simulate this effect. However, it's not transactional. It doesn't guarantee. It's ideal if we can develop the new feature to have multi-table replication instead of a single table replication in the transactional fashion. Then we can achieve this goal. The last one is selective replication to support partial time travel. What I mean is, right now we replicate every snapshot, every version from source to destination. However, it may not be necessary, especially for the table that has so many changes. Like some tables, they have changed every several seconds. Do you really need to have so many time travel capability? Probably not. Therefore, we just want to capture the key, especially for the snapshot that are already optimized, that's compacted. We can avoid copy the small files. We only copy the compacted, optimized information to destination first. The latency is much slower. Second, we still don't lose much because the compacted version, they capture all the data. Okay, so this is takeaway and our conclusions. First, in order to guarantee the data integrity, we need to make sure there's a coordination, especially between the storage and also the catalog service. Second, we want to safeguard the data corruption. This is critical. Once the data is corrupted, it's very hard to recover. And in order to do that, we actually use the access control to make sure the source table is a source of truth. All of the write from application only work on this table. And the secondary table, it's only used for replication. Only replication job can modify that table. The replication job does not modify source table. It just read only. And we also want to optimize the number of snapshots. This is very important because by reducing the snapshot, we can reduce the latency significantly. On the other hand, application team, they do want to keep a lot of snapshot. So we need to see. I think the selective feature should help this situation a lot. The last one is group the dependent tables. Basically, we group the tables that depend on each other as a replication unit and build a pipeline on that. There are multiple benefits. First, it's like we can make sure, okay, once we finish replication, all of the related tables that are available, then the application, they works. Second, actually it make it very flexible. For example, for one group of table, we can replicate from region A to region B. But for another group of table, actually we can use the same solution, start to replicate from region B to region A. Therefore, it can accommodate a lot of scenarios we want to do. It's not just for DR. It can be used for other, for example, to save the cost, like start the compute in a different region, kind of things. Finally, it's designed for uncertainty. The Iceberg DR is not stand by itself. It interacts with a lot of other systems. For example, it requires a catalog service. It uses network to transfer large amount of data. So actually, it interacts with other applications. Also, there are a lot of problems that potentially could happen. How can we recover as soon as possible? How can we detect the issue happening as soon as possible? And also, for example, it's possible our cloud provider has temporary outage that causes the issue for us. How can we identify the root causes quickly and reach out to fix those issues? So once we have all of those scenarios covered, then we can ensure our solution is solid and minimize dependency whenever it's possible. On the other hand, if we have to introduce dependency, how can we monitor, be able to tell which component is having the issue? So the granularity of monitoring is very important. Okay. Yeah, this concludes our talk. Okay, sure.
Hi, I'm Praveen.
Hi, my name is Zahid. I have a two-part question. And the first part is, once the failover happens, do you reverse the direction of the replication so that in the case of failback, you can go back to your original site? And the second part is, are you able to quantify the cost of running this secondary DR site? I mean, if the primary site is X dollars, what does it take to run the secondary DR site in relation to the primary one?
Yeah, I will answer the first question. Praveen, maybe you will answer the second one. So the first one is for application. The application need to be DR ready, which means they should not hard code region-specific information in the code, right? That's the first thing. Second, when we have the configuration, the endpoint is not region-specific. It need to be global. Therefore, as a platform, we control the global endpoint map to which active region. Therefore, applications, they can be ignorant about which region they are running. In this way, actually, we control the switchover and failback. Application team, they just need to monitor, make sure the application running fine, but they don't need to make much change.
Sure, but at the replication level, you reverse it back once the failover happens?
Yes, we can. Yeah, we have verified.
So, yeah, we do have both the failover and failback. I think that was one of the topics you mentioned, that we have to reconcile, so it's all, we should be automated as well, right? Now, regarding the cost aspect, right? I think this is the biggest deterrent for most companies to say, hey, why do I need to spend twice the money for something that you would have maybe once a year, or maybe not even that, right? I think this was on top of our mind as well all the time, but considering that it is important and for whatever good reasons, right? The cost turns out to be obviously the storage and the compute cost. The biggest factor that you mentioned in one of the slides, right, that the egress cost, if you're in the third-party provider, that you can eliminate it maybe if you're not there, right, if in your data center. But other than that, there's a cost of compute to just replicate them. It's just a network cost plus storage, as you can imagine what that could be. So I'll leave it at that. Yeah.
Yeah, thanks for sharing this wonderful architecture. How are you handling the compaction? Because your primary region compacted files are already there in the secondary. You don't have to actually replicate a compaction snapshot. How are you handling that, or you're still considering that as a future one?
Okay. Yeah.
Okay. Yeah, our current solution is we just copy all of the versions. So which means we do copy the data twice, like you pointed out. That's a good question. That's why we propose to have selective replication. Instead of copy all of the version, all of snapshot, we can just copy the compacted version. We don't need to copy all the small files in the middle. So that will be really good optimization. I think that's the next step we should work on. Yeah, thank you.
Sorry. Can you talk more about the replication lag? You said like number of snapshots, but I wasn't clear how you would know that from the source and destination, if there was.
Okay. Because when we read the catalog service as the source region and also catalog service of the destination region, we know the specific version, right? From version, we know all of the file involved in between. That's how we can get those information, has a list of the file.
So only on write do you know? Like if it's down for 10 hours, you don't know until that first write happens, that there was a big gap.
Yeah, if there's a big gap, basically we consider it's a table diverge. Then we just do the full table copy. And we want to avoid this. Full table copy is quite expensive, especially for really big table. That's why we focus on the incremental copy and avoid the data divergence. Yeah.
What about if you're in AWS, there's an S3 copy API that basically doesn't involve copying the S3 object, but kind of links it. Is that possible, or does that not work?
So I'll take this one because I think we've proposed a couple of approaches. Second approach is basically a continuous replication where you could think of really using cloud-specific APIs to do the replication. That leverages the high throughput networks to copy and so on and so forth. It's definitely a big plus to just use those APIs and push it forward. And I would think of it as two parts, the continuous and the batch, right? And you could still, if the cloud provider is providing a batch way of giving you APIs to replicate it, yeah, that would still plug into it and then still work through.
I think S3 copy doesn't involve copying twice. It's kind of like a register operation.
Are you talking about the multi-region access point? Yeah, if that's the case, as I mentioned before, there's no cooperation between the catalog service and also S3 copy. Then it could happen is, okay, the catalog service already replicates the new version to the secondary region. However, the corresponding data file and metadata file are not fully copied. In this way, actually, when someone reads at secondary region, it's not complete table. Basic table is in the corrupted state. That's the danger. That's why we don't recommend it. Like if you want to use, another issue is the multi-region access point. Every read will use the access point. Therefore, it introduces additional cost for every read. And it only works for AWS. If you want to apply this data to a different cloud provider, you have to rewrite every file because it's not absolute location. The multi-region access point, it's a proxy. So there are a lot of like overheads involved when you use that. I mean, the benefit is you don't need to develop your own solution, right? You can just use configuration, use a cloud service, then you put things together, it's working. But there are a lot of edge cases it's not handled correctly. For example, for incremental copy, you need to know what's a file need to be replicated, and also you know when that replication finish. That's important. When it finish, you need to verify the integrity for those copies, and then you can update the catalog service. This is very important. The atomic commit guarantee once you expose a new version to the reader can read the correct data.
Hi, I'm Anjali. This is around deletion of old data. So in your primary region, do you have like cron jobs or processes that delete older snapshots? And do you run a copy of the same sort of code in the secondary region to clean up the secondary tables?
Oh, yeah, that's a really good question.
And maybe I can add a sub-question there. The reason I ask this is, what if there is bug in that deletion code? Then that basically same bug applies in the secondary region, right? If you are under deleting data, let's say, or over deleting data, and you are using same janitor in code, that same bug will propagate to the secondary region.
For the bug, I think I will find more what you mean. But the first question is, okay, you run the table maintenance, right, periodically to either optimize or expire the old snapshot. That's very important for the performance. Basically, the replication actually will replicate all of this to the secondary, so you don't need to run the same update in secondary. This is very important. First, it's like because we replicate everything, every change to the secondary, therefore there's no need to run this maintenance job on the secondary. This way, we guarantee only replication job can write to the secondary. Therefore, we can guarantee the data integrity in the secondary. This is very important. If we allow the table maintenance and also the replication both run in the secondary, we cannot guarantee data integrity.
Then would you allow older snapshots to accumulate in the secondary?
The replication code itself will clean it up because it knows what's the valid snapshot, what's a valid version. Therefore, once it finish replication, once it finish commit to the catalog service, it will clean up. So it's in a single, in this way it's consistent. Yeah, for the bug, I'm not sure what's the bug you're talking about, so I cannot fully answer. We can discuss offline for your question.
One more question.
Yeah, hi, my name is Shailesh. I have a question specifically around incremental replication. How do you handle the case where the snapshot which had to be used for next replication gets purged? Like if table maintenance happens proactively on a table and you don't have the snapshots via which you want to continue incremental replication. Essentially, how do you coexist table maintenance and replication working at the same time?
Can I reframe your question? You mean if the table maintenance removes those snapshots
Yes.
before
Before replication was able to basically use those snapshots to replicate the data.
Yes. So that's also the cause of the table divergence, right? So we have to do the full table copy because whatever that's needed to be replicated. So basically, it's like it's broken. There's no way we know for sure we can correctly do the incremental copy. Our solution is we make sure they introduce some cooperation between the table replication and also the table replication. That's also another reason why we want to push for the real-time replication. Whenever change happens, we can replicate in few minutes. Then the chance for this to happen is very, very little. And we don't schedule the table maintenance every few minutes, right? So that's why our top one performance metric is reduce the latency. If it's very small, a lot of problems, they do not exist.
Just a follow-up question to that one. Um, Essentially, how do you handle the concurrency control between your table maintenance and your replication?
Actually, there's no
The
real.
specific scenario is, how do you ensure that a snapshot expiry doesn't pull the rug under the replication when it's trying to replicate?
Mm,
I think in general, like what we try to do is, and this is probably true for many, we want to keep snapshots, right? For a good reason. Time travel is a good reason. We want to go back and do corrections. So we want to make sure that the table management does not clean up the snapshots, let's say, for a good amount of time, maybe a few days, as an example. And we try to keep the replication going almost close to real time as possible, right? So don't run into this kind of scenario where, hey, you know what? Our table management cleanup is faster than our replication. So that scenario is rare. But like she said, if we ever run into these scenarios, right, where somehow the TMS kicked off and is cleaned up your snapshots, we didn't replicate it, it triggers a full table copy. Like we have lost the lineage now. We will now have to do a full copy. There are other strategies we are thinking of to do this kind of thing where we are somehow able to, by the way, when we replicate it, we do make sure that, hey, you know what, if the data files already exist, we don't copy them again. So if indeed there was good amount of data already in place, your full table copy also should be not as slow. It should be fast enough, right? So that's the premise we go with right now in the system.
Thank you guys. That's the end of it.
yeah,
So
thank
you have a